Okay, we're back inside. My neighbor decided to start mowing his yard out there right now. So we're back inside the house for a little while. So kind of taking a look at the key to the homework and kind of a discussion about that. The beginning part of this is fairly straightforward in that you were just kind of looking at plugging in the upper bound and then calculating the area. I did go over here for each of these areas and went ahead and calculated the kind of the net area for each of the sections, which we made it really easy for you guys in that each of these areas was equal to either 4 or -4 kind of as we were going through the area under the curve. So that was fairly straightforward because the idea here is initially that our accumulation function is the net area in between certain values as we're looking at it. Now, I'm going to take out those shaded areas so that for the first problem that we're looking at, let's kind of talk about what the area would be. Our upper bound here is 2. And so our input of, we're trying to calculate h of 2. H of 2 or h of x is the accumulation function from -2 up to x, whatever your input is. So from -2 to 2, so we're starting here at -2 and we're going all the way up to 2. So it represents the area under the curve from -2 to 2. And that's why I did 4 plus 4 and got 8 for that value. Now, if I was going to do, let's change to a little darker blue so that we have it for the second one. Now we're going to go all the way up to 8, okay? Which, of course, you can't really see that now that I've highlighted it. Let me take that out. So if I want to go all the way up to 8 now, what we want to do, let me do a little bit lighter here, is I still want to start at -2, and I do want to go all the way up to 8. So that would include this area. It would include this area right here, and it would also be this net area down here. So the idea, remember, is that whatever is above is added, that gives you a positive accumulation, and whatever is subtracted is the bottom, where your rate function goes below. So notice that in this one I did 4 4s added together, and then I subtracted a 4. So that way we had the positive accumulation up until we got to 6. Excuse me. And then we had negative accumulation coming down all the way up through the 8 that we had. All right, so now in general, the idea that we're taking a look at is that the derivative of f of x, or h of x, is going to be the derivative of the definite interval. So this part right here, this find h prime of x, is simply us illustrating the fundamental theorem of calculus, that the rate function is the function that is inside of here. And so that when we want that derivative, then the rate function is what we're going to use. The only thing that's different is that our rate function, when we have it inside the integral, we have that placeholder variable of t. And so what we're doing is saying that we have a function that is a function of x, the upper bound. When we take the derivative, we would get that rate function inside, but our variable we took the derivative with respect to is going to be the x. So it ends up just being f of x. That's a key. I mean, I can't star that enough because all of the questions that we've been asking you about a function, about where it increases and where it decreases and things like that, you have to have this key fundamental theorem of calculus concept down so you know how to use the function f of x that I'm given. Like, for example, okay, we didn't ask you for this, but something that I could certainly come in, I might ask you, when does h of x increase on the interval from -4 up to 12? And so what you would have to recognize is that we know that h of x increases when its derivative is positive. So in this problem, we would have to first recognize that the derivative of h prime of x is f of x. So the function that I have here is the derivative of h. And so as we are looking at and answering this question, our answer would be h of x increases from -2 up until 6 because h prime of x, which is equal to f of x, is greater than 0 on that interval. And so that's kind of the big idea about the fundamental theorem, is making the connection to this accumulation function and its derivative and where that rate function is. All right, so now sliding up and going down to the bottom, we're now getting into something that I think is super important for the idea of how we're going to make a connection between antiderivatives and these definite intervals. Remember that the antiderivative is the general antiderivative from the indefinite interval. But now we're going to start to make that connection, and this is leading to part 2 of our fundamental theorem, which is how the antiderivative is related to this. So the first thing that we did in number 3, it just asked you to find a formula for g that did not include integrals. And one of the things that you would again remember is that this g is the net area under the function f of x equal to 3x plus 5. So we would take that rate function, and you'll notice that over here, I went ahead and I basically graphed my g of x, g prime of x over here. Remember, g prime of x is equal to f of x. Maybe I should add that in so that we have that. So g prime of x is equal to f of x, which is my 3x plus 5. So that's the key idea here, is that we graph our rate function and we're looking for the area under the curve. Now, the area that I'm looking at here is geometry. So in this initial foray into calculating a formula for this, I am basically coming up with the area of this trapezoid. And reminding you about the area of a trapezoid is going to be base 1 plus base 2 over 2, the average of the bases, times the height of the trapezoid. So in using that to help me come up with my formula, you've realized that base 1 is going to be your, let's do green here. So base 1 is going to be this 8 because that's the starting value. We're starting the area at 1. And so our height right there is going to be 8. So all I did was plug that into my function over here for f of x. So that was my f of 1. Right, so f of 1. And then I am calculating my height at x. So my b2, which is over here, I don't really have a value for it because remember, we're letting x be the variable. So my base 2 in this problem is going to be the f of x, which is going to be the 3x plus 5. So we're going to keep that in a general sense. And so what I want to do is I want to take them and I want to add those two bases together. So I did that over here. I divided by 2, and then I multiplied times the height of the trapezoid. So let's talk about the height of the trapezoid x minus 1. So when you're looking at that over here, what you realize is that right here at this height of x minus 1, hopefully you'll realize, I'll just bring my cursor over here, see if you can see that, that x minus 1 is simply the distance in between the 1 and the x. And so I just did, distances, big minus small, right minus left, that kind of idea. So that's x minus 1, and that represents the height of the trapezoid, which is the kind of the delta x that you're looking at there. So putting those together, and then I simply just did some algebra. So when we look over here at where I have calculated the algebra in 3a, all I did was multiply the average of the bases times that height of the trapezoid, simplify it down, and I got what is located here in green right here, which is the your g of x. Now, a couple of things to notice about that g of x as we're looking at it. That what if I went to take the derivative of that? So if I take the derivative, it's just a polynomial. Notice that the derivative of g of x, this net accumulation function, happens to be 3x plus 5. So one of the main ideas is to recognize that this formula, this net accumulation function g of x, is I'm going to stress that, antiderivative of f of x equal to the 3x plus 5. So the idea of like finding a general antiderivative is kind of the same idea here, that if I was finding an antiderivative of f of x, we would add 1 to the power and then divide by the power. Then we would have the antiderivative of 5, which is x, and originally we would have had a plus c. Now, I'm going to go ahead and kind of add this in like this and remind you that what did we do in order to find C when we were looking at it? That what we did to find the C for a general antiderivative is that we had to have an actual initial condition that we could use. And the idea that we're kind of previewing here in this kind of homework of the next part of the fundamental theorem is that what would be my initial condition? Like, how did they end up with this minus 13/3 that they had there? Well, the idea is that when we were doing this as the definite integral from 1 to x of 3t plus 5 dt, right? If I was calculating that in general, what if I wanted to calculate g of 1? Or so instead of saying what if, let's say what is g of 1? So g of 1, when we're looking at it, would be the integral from 1 to 1 of the 3t plus 5 dt. Now remember that this accumulation is the accumulation of area. Well, if I start at 1 and I don't go anywhere, how much area have I accumulated? I have accumulated 0 area on that. So if I take a look at that, I can use as an initial condition that g of 1 is equal to 0 from my starting point there. And if I use that and then plug it in into my function, oops, so I have to keep remembering where I'm at on my screen, so that the g of 1 equal to 0. So I can find that initial condition. And that initial condition, when you plug it in over here, so g of 1 is going to be 3 halves plus 5 plus c, and that's going to be equal to 0. This is 3 halves plus 10 halves plus c equals 0. That's going to give me c equals negative 13 halves. And notice that that is exactly what we came up with as the constant when I did this calculation using area. So hopefully that kind of gives you a little bit of a preview of the next set of notes that we're going to do, where it's really going to talk about how the antiderivative with an initial condition is going to be related to these definite integrals and how we actually calculate them. All right, and then the final part here, part C, is going to be the how do parts A and B illustrate the fundamental theorem of calculus? Well, the fundamental theorem, part 1, simply says that the derivative of the accumulation function can be found inside of this definite integral, and the only difference that you have is that you are going to change your variable, the placeholder variable, inside to the variable of that you're taking the derivative with respect to, which is the x and the x and the x right there. So your rate function or your derivative is located in here, and the only thing you have to do is change your variable to x. All right, so hopefully that gives you enough that you're going to be working on. Now, the other thing that we're going to do here now is we're going to kind of stop and we're going to let you do several practice handouts to work with this relationship and really get this down before I go to the next part of the fundamental theorem. All right, so will you guys go ahead and complete the handout justifying the behaviors? This is from the College Board to kind of practice this. And then we have several FRQ examples. There are 4 of them that you're going to practice. So work on that for the rest of this class and for the homework, and then we'll come back on Wednesday with the next set.